Anyway, so let's get started with 7.3 polar coordinates. Well, we know that coordinates are something that we use to track, right, positions, like we do the GPS navigation using the coordinates, right, the longitude, latitude. And we're so used to, right, in the past many years, the XY coordinates, and they actually have uh, a fancy name, right? Instead of calling it X or Y, they're called rectangular coordinates, right? Rectangular, going either left and right, up and down. That's all. But polar, uh, and of course, we're not trying to introduce you something other than just trig, and we actually did already, introduce you most of the trig. So polar is something about the angle and rotation. So let's see. So our goal with the polar coordinate is to be able to locate a point in a space. But instead of specifying, say, to the right or left, how many units you're going to move, or are you going to go up and down, right, using X and Y? We don't do that anymore. We're thinking about like how do I put it? Well, you guys know the old-fashioned radar screen, like in those movies, radar, right? The military stuff, right? You know that, yeah, radar. Let's say something. Hopefully, it doesn't come to us, but if something, right? So the radar's gonna have, I don't know, like a needle, like keeps like swaying, right? Was sweeping the whole space, and all of a sudden, there will be a point that keeps blinking, right? Don't you want to know how far that point is away from, let's say like a military facility, right? Or from what direction, right? That's also pretty important, right? So it's coming here or there, right? Um, so that's what you should think about the polar coordinates. So what happens is instead of thinking about the origin when it comes to x and y, the same point now has a name called pole. So it's the pole, right? Like North Pole, South Pole. And what used to be called the x-axis, right? The horizontal axis, the positive one, right? That always goes to the right. Let's call it polar axis. Axis that start from the pole, right? So now you can think about an angle that will be plotted in its standard position. By standard position, I mean placing the vertex of the angle at the pole and line up the initial axis, the initial side, with the polar axis. Now its terminal side will just be like that radar thing, right? Keeps, sweeping out of space. So it starts from the same place as the initial side. It's the polar axis, right? It's going to turn either in a clockwise direction or counterclockwise direction, depends on what kind of angle you want, positive and negative angles, right? But let's say if it turns in a counterclockwise direction, sweeping out an angle theta, and the point they're trying to locate is right around that direction, but having a distance of r away from the pole. That's how you're gonna locate that point using r, the distance from that point to the pole, the angle theta, which is the angle span between the polar axis and that radius kind of thing, right? Or the terminal side. And that's all you find the point P. I know it sounds complicated, right? But sometimes you're better off using the R and theta instead of X and Y. Yes, brother.
The angle is just equal to the y value.
No, the angle will be whatever angle or whatever direction that you be finding that point. For example, let's say again, think about the radar. If this is north, this is east, right? That angle is say 30 degree. on radar they have those, scales, right? You can tell, relatively speaking, how far they are from, the center of the screen, right? Let's say this R is, like, say, 10 miles. So my question for you is there a way to locate a point P if you know that the P is at 10 miles away from the pole, wherever you pole, let's say this is the pole, right? The room is the pole. So a point that is 10 miles away from the pole, and it's in such a direction, starting from the east, turning to the north by sweeping out a 30-degree angle.
Sorry.
If you want, yeah, you can draw a right triangle, right? But you probably don't need that. Just by imagining, it's almost like a bearing. You see that, right? Instead of us starting from the north and east, north and south, you start from the east, right? Going this way if you want a positive angle. But if you turn the other way around, it'll be negative angle. Okay. So now, simply put, the polar coordinates, which uses r in the data, tells you r, which is how far that point you try to study is away from the pole. And the data tells you in what direction. Is it from the south, east, northwest, or southeast 30-degree, northeast, right? Whatever. But of course, it is that angle that makes it a bit harder for you to imagine. Okay. What the best way to get used to the polar coordinates is to use it to plot the points that you're so used to, right, with x and y. Because now if you plot the point x and y in, let's say, 3, 2, right, that's trivial. But might not be that trivial with the polar coordinates. There's one little catch here. They say r is not just a simple distance. It's a directed distance. We'll see about that, in that example, right? But if you understand that r is a distance, that's good enough, right? But you need to be careful later when you get negative r. Anyway, so as you can see that we have 3 points. We're gonna do the first two. There's no need to do the third one. It's the same thing. The first component in that order pair, not x anymore, it's r, which tells you the distance. But see that it could be negative, right? So we'll understand what I mean by negative 2 units of the distance. The angle will be the theta, right? Measured in such a way that if it goes counterclockwise, it will be positive, right? Or going the other way around, get negative. But you have angles could be in degrees or radians. Just to make my sketching a bit easier, on the computer. So I did find some pretty nice, polar graph. So I don't have to draw things and make it, not very accurate, right? That means what are odds that you're provided, a polar graph like that, right, for the test? That means that you're probably not going to be graphing at all, right? But you need to know if I put a point right there, would you be able to read off the R in the data? Right? That's all I want to do. So let's start with the first point where it has to be 3 units away from the pole at a big angle, 315 degree, right? So what I typically do is I'll start from the pole and I'll follow the polar axis. Let's count how many units I want. So if you want, you can go with 1, 2, 3, right? 3 units. But you decide the scale, right? They won't label the scale for you. Let's say this could be 1 mile, could be 100 miles, right? But we need 3 units of the distance. So now where is that point? It could be anywhere along the circle with the same radius, right? But we know the angle, right? The angle has to be 315 degrees. So, and it's positive. That means you're going to go around. And let's say, scroll down a little bit. See that it would be somewhere between 300 and 330, right? So, and it turns out, so I didn't I didn't realize that, they, say they go from 300 to 330, that 30 degrees, right, in between, but they didn't put, like a 5 increments for some reason. They put 4 slices, which means that each slice is, 7.5 degrees, right? But, it happened to work out because we want 215, which is right in the middle, right? That means it will be, somewhere here. And let's call that point A, right? It has a distance of 3 units, the angle 315 degree, right? And by angle, I mean it's starting from the pole axis going all the way around, right? And this big angle is 315 degree, just so you know. Okay. Again, do you see that the process is just like the radar screening the space, right? So before you notice there's a point there, right? You wait for the terminal side to go all around to sweep out. You see that, oh, that point is 3 units away from the pole, and it's in that direction. That's all. Now let's try another point. I believe it's -2, right? The distance -2. And what's the angle? Pi, right? And pi is 180 degrees. Let's get the same photograph, but instead of labeling in degrees, let's go with the radians. And a pi is right over there. So I need 2 units. Again, I'll start from the pole. Follow the polar axis, right? So this is 1, that's 2, right? And what is pi? That means you're gonna go around, right? That is 180 degree, or pi radians. That means you're looking at a point right there. Okay. But how will I label the coordinates of the point? It's not -2, it's 2, comma, pi. Right? But now the question is, how do I find out a point with a -2? This is why they call it the directed distance. No, that's not a middle point. That's the pole, right? First, I go to 2 units away from the pole, right?
Maybe 2, so therefore.
Right. That's actually not the point I was supposed to plot, but I was following the distance 2 units and then the angle, and it lead me to the point that I didn't want. So the question is, how is that -2, comma, pi related to the point over here? And let's understand the directed distance. Yeah.
It's -2, which is start right now.
Start here, go there. You could do that. Well, so now that means, do you see that there are probably multiple ways to understand or label the points, right? Because we know that the coordinates are not physical. By physical, I means that different people can set up the coordinates different, right? So Matteo said that, well, instead of going from that point going around in that direction, start from here, right? Go in the opposite direction and go all the way around, right? So now, but turns out that they have this convention saying that if you're looking at a point with a opposite r, say -r, right, -2, you will reflect that point off the pole to make it on the other side. Okay, that's like turning the angle for another 180. So reflect that point off the pole. So the point that we have to plot is here, and that is -2, comma, pi. So now, simply put, the r is directed distance. It is distance. Whether or not it's 2 or -2, you see that both points are still 2 units away from the pole? It's the distance, right? But You follow the angle to get to the point, but if the distance is opposite to what you want, you reflect that point off the pole. Okay? Or let's say you're gonna expect all the positive distance, right? But then you realize I'm probably in a negative distance. All you have to do, find that point with the positive distance, then reflect it off the pole, right? And reflecting the pole is basically turning either this way or that way by 180 degrees. That's all. Okay. But now we're getting to a point that you say this point is no way pi radians. You see that this point is on the polar axis, right? Isn't that 0 degree? I thought that a point on the x-axis with the terminal side exactly the same place as the initial side, the angle has to be 0. Well, this is why you will always find the polar coordinates or even some other coordinates you have to learn in the future, like spherical coordinates, cylindrical coordinates. They are not unique. By unique, I mean there will be infinite many pairs of coordinate data associated with the same point in the space. It depends on what kind of coordinate data you like. But is that the case with the rectangular coordinates, x and y? So let's say the whiteboard, right? I can fix the origin at the bottom left corner. That's the origin. To the right is x, right? Going up is y. So a point with x could be 1, y could be 2, right? Can you uniquely pinpoint that point on the whiteboard? 1 unit to the right, 2 units going up, right? And that's the point P. Would there be another pair of x and y associated with the same point? I don't think so. But for ordinate data, you do have infinite many choices. Say, can I come up with another pair of ordinate data that represent the same point, but make it a bit easier? I don't like to deal with -2. A point that is 2 units away from the pole, and it's on the polar axis. What could be a better angle than pi? Would you say that point could be 2, 0, right? So again, think about that. Follow the polar axis, get to 2 units, right? Don't turn it off because it's right there. But it might be confusing because, if you don't explain to whoever's reading your work, who knows that you're not putting down the x and y, right? 2, 0. You thought that it's just 2 units to the right and 0 units going up, right? But that's exactly the case, right? That's how it's a coincidence. So things are confusing. It's not your fault, but you need to be aware of. Okay, that's why they're saying that now we are plotting, the coordinates, in terms of ordinate data. All right, so now moving on. And now let's be flexible with ordinate data. I know that this is actually the harder part, right? So saying flexible, they have more options. It might not be a good thing. They say, go ahead and find out a different pair of ordinate data for the point 5, pi/4, such that I want a positive r, but theta will be greater than pi/4, and then in a range of 2 pi to 4 pi, or a negative r, but the angle is still going to be less than 2 pi, or make the r positive, but angle be negative. Start with the letter A. Yeah, Logan? Exactly. The one with the x and y is called rectangular. The ordinate data is called polar. So I will keep the r as positive 5, but how will I change the angle to make it bigger than 2 pi, or still looking at the same point? Yeah, Alex. You can add 2 pi, right? Or subtract 2 pi, right? Or add any multiple of 2 pi, or subtract any multiple of 2 pi from it, right? But in this case, just 2 pi is good enough, right? Now the reason is simple. All the angles that are off by 2 pi or 360 degrees are equivalent. They're called coterminal angles. So therefore, 5 pi/4 is equivalent. It's like a double arrow, right? Double direction arrow, equal sign kind of thing, right? Equivalent to 5 comma pi over 4 plus 2 pi. Now, easy to put that angle in a range of 2 pi to 4 pi. You simplify it, it will be 9 pi over 4. Okay, good, right? So, hey, do you guys realize that this is the lesson so far that you haven't done any trig at all, right? It's just angles. But I guess that this is indeed what we started with, right? Trying to get used to the angles, right? And so hopefully that when you see the test paper, when I see the test paper, it won't be as bad as you thought, because we're trying to, finish the lesson within, like a week or two. Anyway, now let's try letter B. This is actually the tricky one. How would you make the R negative, but you're still looking at the same point? Don't forget that you have two components, right? So you have both the R and the theta, right? You can change them. Well, if you don't see it right away, let's plot it, right? So now, if you don't mind, I'll come back to this, in a minute. So let's go ahead and plot 5 pi over 4 on this radians graph. All right, so I'm going to start for the pole. Right, go to the right along the polar axis. 1, 2, 3, 4, 5. Right. So now I'm looking at the circle, right? This big. So I need to go to pi over 4, which by the way is 45 degrees, right? And I think that it's right in the middle between the pi over 6 and pi over 3. So this is pi over 4. That means I'm looking at a point right there. Okay, so again, it's 5 units away from the pole, and the angle we're looking at is 45 degrees. So this point is 5 comma pi over 4. But if I want negative 5 instead of positive 5, what would that point be? If it's negative 5, but with the same angle. Okay. Right, it will be exactly on the opposite side of the pole, right? So it will be, well, that's going to hard to tell, maybe somewhere here, right? Okay, so it'll be 1, 2, 3, 4, 5. Yeah. If I have a straight edge, I could show you that it's exactly on the opposite side of the pole, right? So that point is negative 5 pi over 4. But unfortunately, this is not the same point I want. How would I change it back? But keep the negative 5. You cannot do the R anymore, right? So play with the angle. So if I turn it back, what's going to happen to the angle? I'm rotating by how many degrees? 180, right? Or pi radius. There you go, right? So you're just adding the pi. So now you're back to the same point, but unfortunately, you're going with negative 5, right? And a pi over 4 plus pi, which is negative 5, yeah, by pi over 4. So this is the way that you can get yourself, oh, that's awful. The same point, but unnecessarily complicated, coordinates, right? Negative 5 is positive 5 and a bigger angle, right? But we could do it. And again, there are infinite many choices of R and theta for the same point on the coordinate system. For the polar coordinate system, but for X and Y is unique. All right. Any questions so far? You good? It's just like, a few more rules, right? Get used to the radians, that kind of stuff, right? Nothing too bad. So now, if you wonder, I just don't like polar coordinates, right? Just like, I just don't like radians. I guess that in the first month, right, of the semester, whenever I ask you, hey, what is pi over 2, right? How do we deal with sine of pi over 3, right? So you're probably gonna always convert pi over 3 to 60 degree, right? So it's okay, if you're still doing it. So it would be nice that we can always convert from the ordinate data, right, the polar coordinates that you just don't like, back to the rectangular coordinate system. We can do it. We can actually go back and forth, just like always going back and forth between our radians, degrees, and our tests. So we have the first two equations that tells us how you can go from ordinate data, which are given, back to x and y. You can calculate what they are. Okay, so this is from ordinate data back to polar, sorry, back to rectangle, right there, right? Now the second set of equations takes you from x and y to ordinate data. Okay, for some reason, if you want to go from the rectangular to the polar coordinate system, you can do it by finding ordinate data. Okay. But let me point out that you don't have to remember the first set of equations, because this is actually what you already know. You guys remember in 6.5 when we deal with solving equations, right? And I asked you to get all the angles, right? All the possible solutions. And the way I choose to do it is to, expose you to the towns of like a unit circle, right? But to plot a point on a unit circle, instead of labeling the point with like x comma y, we say the horizontal coordinate is cosine theta, the vertical coordinate sine theta, right? Isn't the same thing here? The horizontal coordinate is cosine theta, right? Y is sine theta. But you say, what happened to R? On the unit circle, R is 1, right? But in this case, and it doesn't have to be unit circle, right? It could be 10, 20, units of distance, right? So that means, no extra effort whatsoever you need, right, to memorize those two. What about this one? This is simply saying the pole, which is the origin, and you have a point located at x comma y. What is the distance between that point and the pole? But isn't the hypotenuse of this right triangle, right, which is x squared plus y squared, then first take the square root to get r. No ambiguity whatsoever, and that's how simple it is. That means only the last equation, and you know what? This is probably after almost 30, 40 minutes, right? 30 minutes, they'll be doing a trick, right, in this class. That means you're going to have to find me the data given x and y. How would you do it? Given x and y, find the ratio, but it's the tangent data equals to that ratio. How'd you get the data? Inverse can, right? And you don't have to do it by hand. Use the calculator, right? But unfortunately for the angle theta, there will be some subtlety, which I'll show you in a second. Let's do the easy, conversion. Going from polar to rectangular, it's super easy. All you have to do is calculate the x using r times cosine theta, right? In this case, the first component is r, second component is theta. So you have 3 times cosine pi. So no need to memorize those special angles anymore. Use the calculator, but make sure that in radian mode, if you're seeing those radian angles. So cosine pi is -1, so that's -3. And y is r times sine theta, 3 times sine pi. And sine pi is 0, so that's a 0. Okay, therefore the rectangular coordinates in the form x comma y. Well, the same point will be -3 comma 0. All right, that's it. All right, so let's do the letter B. Same thing, right? So now I don't have to write down the r cosine theta or sine theta. You know what they are. Say it again. What's on the calculator? If you're looking at pi and it's not a degree, right? You see that they have to put a little circle to say that's a degree. But if you don't see a circle, that's in radians. Yeah. So yeah, you have to still be careful with what angle it's dealing with. So r, which is -10, please keep the negative sign, because r could be negative, right? Times cosine of pi over 6. You don't need to know that pi over 6 is 60 degree anymore or 30 degree anymore. Just type it up, right, in the calculator. But I know cosine 30 is radical 3 over 2. This is -5 times radical 3. Y is -10 times not cosine, sine of pi over 6. Sine pi over 6 is 1/2. This is -5. All right, so you're looking at the rectangular coordinates for the same point, -5 radical 3, comma, -5. Okay. And again, turns out that if someone simply tells you, the coordinates of a point without letting you know whether it's rectangular or corner, there's no way you can tell. Because guess what? Is it possible that theta could be -5? You think about angle theta that's -5. -5 radian. It's possible, right? Because theta could go the one way or the other, right? That means just letting you know they have two numbers, -5 radical 3, -5. Do they have to be x and y? No. R could be negative, theta could be negative, right? Theta could be all real numbers. So again, please make sure you read the instruction in the test. Know what you're dealing with. Do they give you R and theta, or do they give you x and y? So now let's take a look at the tricky version of the conversion. So going from x and y back to r and theta. All right, so we have x, that's 1, right? Y is -3. So you take the first equation here to get the r. R is square root of x squared plus y squared. That is square root of 1 squared plus negative radical 3 squared, right? Which is going to be 2. Square root of 4. Any subtlety? No. It has to be 2. Right? That's why, R is still the easy thing. It is the angle theta. So we have the angle theta coming from the tangent, which is y over x, right? So that will be negative radical 3 over 1, which is just negative radical 3. And then we invert the tangent, right? So we put tangent inverse of negative radical 3 in a calculator, right? So now if you try it, you're in degree mode, you get exactly -60 degree. But type it up, to convince yourself that's the case. Or if you like radians, that's -pi over 3. All right. Now let's do a sanity check. A point associated with the angle -60 must be in which quadrant? Think the -60, that means you're gonna go down, right? The angle's gonna go in a clockwise direction. So it'll be in a fourth quadrant, right? But using x and y. Positive x, negative y, is that point in the fourth quadrant? Yes. That means this time the angle is correct. But what if? So if this is the point P, what if you do the same thing for the point Q, which is -1 comma positive radical 3. Can you carry out the same calculation for the angle theta for the point Q? Go ahead, do it. Find out the angle theta given the x, which is -1, not +1, but y is positive radical 3 instead of a negative radical 3. Anyone got the answer for the angle? Or do you see the problem? Something that just doesn't make sense. Because I'm sure that you see that just by switching, right, the sign, but I'm still getting the same exact ratio. Do you see that? Y over x is still -3, negative radical 3. That means if you type it up, 100% you're going to get the same exact angle, -60, right? But -60 is in the fourth quadrant. Is the point Q in the fourth quadrant? No, right? That's in the second quadrant. So now, guess what? There's something wrong with the angle theta. We have to fix it. But how do we fix that if the angle is in the fourth quadrant, but I want that angle in the second quadrant? You reflect it. Now, when it comes to angles, what would you do mathematically to reflect the angle or reflect the point? If the point's somewhere down there, you want to reflect off the pole and let it go up to the second quadrant, which you're going to do to the angle. Okay, Malika said pi, right? Or 180, is that what you said? All right, so turns out that you're gonna rotate it either this way or that way by adding or subtracting 180 degrees. You might say, well, you're literally changing the angle, right? Would that be safe to do that? Thanks to the tangent. Any angle off by a multiple of 180 is the same from the point of view of tangent. The tangent has a period of 180 degrees, right? Simply put, if you ever see functions like tangent theta plus pi, you know what? It's pointless to add the pi because tangent doesn't really, see any difference. It's the same thing as tangent theta. So you can always add or subtract any multiple of pi or any multiple of 180 to get the same angle. And this time we're going to take advantage of that and say, well, we are getting the angle straight from the calculator, right? But that's not good enough. We need to add 180 degrees to bring it to the second quadrant, right? That means it's -60 plus 180. You're getting 120, right? Or 2 pi over 3 radians. And this is the subtlety. That means you are sometimes getting the wrong angle straight from the calculator, but it's not super wrong. It's just 180 apart from what you want, right? And how would you know? Make sure you know which quadrant that point has to be in. If the angle points you in the wrong quadrant, you need to fix the angle, but you see how easy to fix, right? Just add or subtract 180, and that's all I have to do. But when you add or subtract, it's based on the angle. If you want an angle to be second quadrant, then, figure it out, right? By either adding or subtracting, most likely adding. But it turns out that we can we could not only convert coordinates for point. If you don't like the point given in the xy coordinates, you can write it in r theta or the other way around. We can even convert equations or graphs from either the polar coordinates to the rectangular, or even from rectangular to polar. For example, here we have two graphs, right? Now, in terms of the rectangular coordinate system, I think that it's fairly easy to tell what shape those graphs are. Like letter A. What kind of shape is that? You would have plotted. What does that graph look like? A linear function, a straight line, right? You guys see that? It's just not written in a standard form. What about the second one? Quadratic, right? It's a circle. And it's a circle shifted
To the left,
say,
or I mean, down further.
going down, yeah, so it's just shifted down by 1. So the center is at 0, comma, -1, right? Good. So you see that now with the rectangular coordinate system, those graphs are easy to tell, right? You might say, what's the point about converting them into the polar coordinates? You will see that it's completely pointless to do that for letter A, but because we can't do that, so you might have to do it for the test. Well, you'll see that letter B, it will be a lot easier to use the polar coordinates. All right. So let me do that real quick. Now for letter A, see that since X and Y could be represented by R cosine theta, R sine theta, just go ahead and make the substitution. So when you see X, replace it with R cosine theta, then Y, replace that with R times sine theta, right? Now, technically speaking, this is it. But somehow they wanted to express the R in terms of theta. That means isolate the R. You could do that by factoring out the R. So 3 times cosine theta minus sine theta in the parentheses. So you divide out, right, this part. You're looking at R equals to 6 over 3 cosine theta minus sine theta. Okay. Now, of course, there's no way that this looks like a straight line, right, in a polar coordinate system. But magically, if you plot it in decimals, it's going to be a straight line. Okay. Now let's try letter B. It's the same thing, but you might hesitate since it might be slightly heavier in algebra, but you'll see that after a few lines that it's not as bad as you thought. So again, we see X, right? We're gonna replace it with our cosine theta, and you need to square it plus so Y, which is R sine theta, right? Just square that as well, equals 1. And let's expand it. So this guy, you're going to square both R and a cosine theta, right? Now, for the second term, you will have to expand it using the perfect square trinomial. The first term is going to get squared, just like the R square sine cosine square. R squared times sine squared theta. And then you have the middle term, which is 2 times the first and the second term. It will be 2 times R sine theta plus the last term 1 getting squared, right? So it's still 1, right? Equals 1. And the 2 1s cancel. And now, look, that's the kind of a interesting combination that you are probably very used to now, right? If I factor out R squared, you see it better. Cosine squared theta plus sine squared theta, right? I factor R squared from the first 2 terms plus 2R sine theta equal to 0. What do you think this guy is? Cosine squared plus sine squared is 1, right? Gone, so you're left with R squared plus 2R sine theta equal to 0. You see that you could further simplify it by factor of R. It's like doing the verification of identities, right? Factor of R, you get R plus 2 sine theta equal to 0. Well, that's a product, right? It's a 0 product. That means the only way it works is either R equal to 0 or R plus 2 sine theta equal to 0, which means that R is -2 sine theta. So, I mean, you might say, well, still, it has R and theta in it, right? It doesn't seem as good as, the original version. But you have to say that algebraically, this looks a bit simpler than the original quadratic form. But you have two possibilities. What does that mean? R equals 0. It's on the pole. It's the pole itself, right? Any point that has 0 distance away from the pole, doesn't matter what angle theta it is the pole, right? So now if you go back and put this into the in decimals and plot it, it will be a circle, as you know, right? Just like before. But that circle has the origin on it. So the pole is included in the second equation. So there's no need to keep both of them. Let's just keep the fancy one. Okay.